Well, welcome everybody to the Institute of Physics East Anglia Branch lecture series. I'm Colin Ribson. I'm the chair of the East Anglia Committee for the IOP. And we're looking forward to our lecture this evening, which is on Listen to Your Process with Federico Alberini and Francesco Maria Codicino. Just a few things on housekeeping. Yes. If you've got a question, type it in the Q&A box, and we'll try to get round to all of them at the end of the talk. The talk itself will last a little under 40 minutes. We'll be done by about 8 o'clock, if not before. Finally, this lecture is being recorded and it will be uploaded to the IOP, what's called Region and Nations YouTube channel. So you can enjoy that or share it with your colleagues and friends in the future. Just to say a few words about our speakers. The company Rheology has, Rheality I should say rather, is a spinout from the University of Birmingham in the UK and has been developing a novel sensor technology for real-time measurement of rheology in liquid manufacturing industries. And our speakers this evening are the co-inventor, Dr. Federico Alberini, an acknowledged expert in rheology measurements and liquid product formulation. And also Dr. Federico Alberini will be joined by Dr. Francesco Maria Codicino, Rheality's co-founder. And we look forward to their talk, listen to your process very much, and I hand over to them. Thank you. I'll see you later on for the Q&A.
Thank you, Colin, for the introduction, and thank you for having us this evening. As you said, Rheality is a startup and it is a spin out of the University of Birmingham. We are a young company incorporated in January 2020, so in the middle of the pandemic. And the name is clearly rheology and real-time reality, the reality of what goes on in a pipeline. So we played with the wording here. The presentation will have two parts. One more, let's say, more technical, led by Federico, and the second part led by myself, and then we'll have the Q&A. So that's the format. So Federico, please go ahead.
Okay, if you share the screen with the presentation.
Oh yeah, that could be useful actually. Righty-ho, and you see the main screen. I have to screen, so I'm just making sure you're seeing the presentation screen.
Yes, yeah, is the right one.
Yes, and I'll try and click.
Yeah,
and
okay.
Here we go. Perfect.
Okay, I will tell you. So yeah, welcome to the talk. I'm Federico Alberini, and I'm one of the inventors of Rheality. So I'm going to talk about what Rheality is and what Rheality is trying to achieve. So in terms of the application itself, we are quite interested on the manufacturing of liquid products. We start obviously with the idea of use this technique to have something that was not, let's say, available yet in the market. Because what we know, if you want to have a successful manufacturing, you need to have 4 key components. One, obviously, a good final and consistent product, which sometimes can be quite challenging due to the variability, for example, of the raw material, but also of the process condition that can be influenced by many different things. Obviously, a good manufacturing practice is something that you wish as well. And one that we are really interested in trying to provide something more is to achieve a nice and a very controlled strategy to ensure this product consistency. With this, it sounds, let's say, obvious, but it's something that in industry sometimes is very challenging to achieve. And obviously have built-in redundancy and flexibility. So yeah, please change slide. What are the challenges in the manufacturing of liquid products, and in a way for Rheality, the opportunities? So when you process liquid products, most of the time you have very complex products, which are obviously made of different ingredients, sometimes different phases. And obviously all these complex, let's say, structure or microstructures basically give the final performance of the product, and obviously is what make challenging the consistency of this product. Most of the time, to control and measure this microstructure, obviously there are a lot of analytical tools that are employed to measure the different properties, for example, of the fluids, which could be obviously one of, we are interested in rheology, others, there can be many others. However, to achieve such measurements, you need a lot of time. And obviously the time is what in industry is not available, or is not in a way willing to waste. And obviously controlling this microstructure is really important, because as I mentioned, will control the final consistency of the product, which in a way is the macrostructure of the fluid. Obviously, the goal of Rheality is then to do all these things inline and online. And how this can be done? Obviously, as I mentioned, rheology is one of the key measurements that can be used to control all these linkage between the microstructure and the macrostructure. Please change the slide. So to who is not familiar, so rheology, so from a textbook, what it is the study of the flow of matter. Often viscosity is what most of the people knows. However, viscosity is not the only information that rheology provide. Viscosity is, let's say, the rheological parameter that describe a particular class of fluids, the Newtonian, only the Newtonian fluids. However, most of the real liquid products, they don't fall in this class of fluids. So viscosity is not always the best parameter to describe, let's say, the rheology of what are called non-Newtonian fluid. As I mentioned, generally, rheology is a very time-consuming measurement because taking a sample, going to the lab, taking the measurements, even if you are really good and very fast, cannot be done in less than 30 to 1 hour, 30 minutes to 1 hour. However, this measurement can provide really rich information about the fluid. But at the same time, and this I'm talking for standard offline measurements, it can be challenging in particular when fluid with a complex structure. So, for example, fluid that has multi-phase. A simple example can be an emulsion, or a fluid which is aerated. In that case, also offline measurements can be quite challenging. And what we are trying to achieve with Rheality is to overcome all this problem and provide information about rheology for all types of liquid products. Please change. So how the technology itself works? So the technology is it's relative simple from the understanding point of view. So there is, as you see, A is the, let's say, the brain of the technology, which basically inside there is all the hardware electronics. Then the electronics is simply connect to a sensor, which is a piezoelectric sensor. And this piezoelectric sensor is placed on top of a probe. And this probe acts as, I would say, a sort of antenna that basically capture the measurement, or the, let's say, the events that happens inside the pipe that you can see with the here at the bottom of the slide. And then you can imagine that the fluid comes in from B and going out from E. Basically just the flowing of this fluid that we are interested inside this pipe section, hitting our probe, provide these rheological measurements. The great advantage, obviously, is that the sensing part is never in contact with the liquid, and this is allowed us to work with pretty much most of the type, or most of the aggressive fluids that can be used, because the material of the probe can be made exactly with the same material of the piping, despite is a metal. So please change the slide. So the other good thing of the technology, so we use this sensor technology that is a well-established technology. So it's not a completely new sensor. So it's a passive acoustic sensor, which often is confused with ultrasound. So the main difference is with ultrasound, there is a receiver and a detector. With the passive acoustic, what you have, you mainly have only a detector. So you overcome all the problematics that you have with ultrasound. The technology is quite plug and play, because at the end, as you've seen in the previous slide, you can fit easily in any pipeline. You just need to change a small piece of pipe with the pipe provided by us with the probe. It's relative low capex and opex requirements. And so it makes use of big data that we are going to talk in the next few slides. And obviously, our aim is to basically provide a technology that can enhance the Industry 4.0. Please change. So to simply explain the basic principle of the technology, so I decide to basically show you some simple computational fluid dynamics that we have done with colleagues of the AMTECA team of the University of Birmingham. So what we've done, we simulate the flow inside the pipe section that I showed you before. And we basically try to provide a physical interpretation of what is going on the measurement itself. So please change. So imagine this image corresponds to the cross section, the section of the pipe that I showed you before, exactly in the middle. So as you can see, from the left is where the fluid is coming in the pipe. Then the white rectangle is the part of the probe that is extruding inside the pipe section. And what we basically got from this study is what we basically believe was happening in the measurement itself. So what happens is the fluid flow hits let's say the probe inside the pipe, and obviously if you remember, if you've done any of the basic fluid dynamics in your studies, so the fluid flow is pretty dependent of the apparent viscosity, or more generally the rheology of the fluid that is flowing inside the pipe. So in simple word, what happens is the distribution of the velocity that in this slide is represented by the different colors change according to the rheology of the fluid that is flowing inside the pipe. This what it means. It means that then the flow that is developed in the proximity of the probe is, let's say, specific to the type of fluid that is flowing. And this is basically translated in different distribution that you can see on the right bottom side of the slide, different distribution of pressure on the face, in this case of this square probe. And this is what generate the signal for our sensor. So please change slide. And so if we see this process in a transient state, so in time, for example, and we in a way measure the average pressure on the area that I showed you before, you could see that this pressure oscillate quite a lot in time. And this is practically it's what generate the signal that our sensor reads. Okay, please change. So these are on the top right. You can see a snapshot of an example of the raw data generated by the sensor. So it's basically a classical voltage sensor in time. Obviously, this signal is a very rich signal with a lot of information, and in particular because the technology that we use is a multi-frequency sensor. So we record up to 500,000 hertz. So we have a quite wide range of frequency of measurement. And this is why I'm showing on the bottom the same data in a frequency regime. And basically, all this information obviously are very rich, but at the same time are very heavy. So what we can do with this such information, please go change. We develop this spec, let's say, Rheality outputs, which we call Rheality Rheological Factor, RRF. And what they are is a simple sequence of parameters that basically are used to describe the complex, rich, and heavy frequency distribution data that the raw data are provided by the sensor. This sequence is a way to basically identify the rheological fingerprint of the desired liquid that we are analyzing. And these 10 parameters can be used in a much, let's say, easy way, because you can think about that the first raw measurements is for each instant in time. We are talking about 500,000 data, and these 500,000 data are reduced in 10 parameters. So also from a computational point of view, this is open a lot of doors. Please change. So to explain the rheological, the Rheality Rheological Factor, you can think about a DNA sequencing. So you know that every one of us has a different DNA sequencing, and then there are not infinity nucleic acids. So it's just a sequence of this nucleic acid. And the RRF in a way is similar. So we have these 10 parameters that they can have a different intensity, but the combination of different intensity describe a particular rheological fingerprint. And this information can be used live and inline pretty quickly. Okay. So the advantage of using the rheological reality factor is then that these raw reality measurements can be fed easily to machine learning algorithm to train, because obviously we face that different consumers have different needs. So no not all wants to have a rheological characterization of their fluids, but they want a specific process parameter to be identified. So we can use machine learning algorithm feeding our RRF data to convert to a specific outputs. At the same time, because the amount of information is not huge, even the raw rheological reality factor can be used potentially in a process control system, because it's like, in a way, to have 10 temperature or 10 pressure, but it's just 10 parameters. And the good thing is there is a drastic reduction of the amount of information, but there is not a proportional lose of the richness of this information itself. Please change. And yeah, coming to my last slide, and then I will give the privilege to Francesco to continue the presentation. So what I would like to conclude from my part is, so what Rheality is aiming is to provide a smart sensing that basically can provide to the industry a real sensor that can really enhance the Industry 4.0. This is because Rheality can provide a lot of information. It's not only about rheology, can provide others that in a way are directly linked to the rheology. And what we aim is to provide a technology that has an efficient communication. So we are aiming to provide a technology that can be used obviously with standard communication, but also with more advanced through cloud or through wireless. And in a way, our aim is also to help industry to do this change, because there is a lot of talk about Industry 4.0, but when then we talk about implementation, is not as straightforward as it looks like. So I think as company, we are closely work with the clients and helping them also to do this step change, because at the end is a big step change. Okay, Francesco, I leave you because I think I took enough of my time.
Yeah, thank you, and I'll continue with a more general view of the technology. So when we were thinking on how to also sort of explain or position ourselves compared to others, basically we ended up with this sort of pyramid, because these are the different layers, or let's say the different levels of parameters, metrics or characteristics that characterize Rheality with respect to, in this case, for example, viscometer. Actually, there is a mistake here. It's not offline, but they're online. So basically, here we made a comparison with two other let's say device providers, and basically when they can, I mean, they are generally good at providing value of viscosity in this band here, so with a sort of accuracy which can also be not exactly to the point. But when we start moving up in terms of just viscosity. We can provide viscosity measurements, and they, as viscometers, they can only provide viscosity measurement, but we can also provide all the rest of the scale. So we can move and up to rheology. We can be used in any pipe with any scale, so that the size doesn't matter. We are not restricted by size. We are not restricted by fluid regimen, so we can also be used in turbulent regimen. We are fluid agnostic, so it can be multi-phase, can be Newtonian, non-Newtonian, and as mentioned by Federico, it's a touchless technology. So the sensor part is external to the fluid, so that in a way simplifies operationally many things, and we are multi-feature, so the single sensor can actually provide more than one measure, probably just because the richness of the signal allows us to extract different features. Okay, so it can be viscosity and rheology, for example. Okay, not just one sensor, one measure, but one sensor, multi features. So in terms of other inline rheology measurement devices, again, now the two competitors here, and that's again through the scale where they are positioned. So basically they can get rheology in line, but they again are limited to laminar regimen. When they move up with sizes, and we'll see with other slides later, when they move up to sizes of the pipe, or in other with fluids which are multi-phase, or with regimen which is turbulent, then things don't apply to those other devices, while we go again the full length. So we are fluid agnostic, size agnostic, regimen agnostic, and so forth. So I just explored a little bit of these concepts now. So of course, the immediate, let's say, the first feature is shifting measurements from sampling offline and measuring offline to inline. So we go from a process that can, in a very skilled and fast environment, can take half an hour every time they want to take a measurement, to up to hours of measuring time offline to by the second measurement. So real-time, inline real-time measurement. So that's one first feature and characteristic. The other one, as I mentioned already, so the sensing part is actually outside the fluid environment. So we have not. So there is no complications with the sensing, with the sensor that can be used. So we can go inside the pipe with any material. So it can be the same material of the pipe, of the process we're dealing with. There is less maintenance. So everything is plug and play. So we can deal with the piping system alone, or with this electronic part alone, depending on with the maintenance needed. And again, there is no. We are not affected by the type of fluid, so there is no clogging, there is no, if it's a harsh environment with high pH, we are not affected by this. So there are lots of benefits to being outside, and we know that other instruments have instead this type of problems of clogging and sensor replacement and damaging, etc. The other accuracy. So basically here, when we go and consider single continuous phase fluids, again, the offline competitors, beside the issue with times of those measurements, yeah, they can. This is just a symbol to say, yeah, they can do it. For what concerns the inline other technologies that are available, again, they can be restricted or by the type of fluid they can operate. So they need, for example, one needs a conductive fluid to work in both situations. So when it's single phase or multi-phase. The other one can work in single phase but cannot work in multi-phase. Well, again, we are agnostic agnostic to that. So we can work with single phase fluids and multi-phase fluids. Again, multi-phase, we are currently working with up to 4 phases, where there is gas, water, viscous oil, and also particulates of solids. So this is just, again, a representation of complex multi-phase fluids. Again, in terms of size and fluid regimen, everyone can work on lamina. When it goes to turbulent, the other technologies don't apply. And in terms of sizing, it doesn't matter for us, really. So there are restrictions on the other technologies. They have upper limits. We're working now on the highest, the biggest size we are working with at the moment is 10 inches. But again, going higher, it wouldn't be a problem. And this is also to give you an overview of the trials you are involved in at the moment. So we have, and this is also testimony of the fact we are fluid agnostics and fluid agnostic to also to working conditions. We have trials in these different sectors, and already working in Europe, UK, and the US. Okay. This is just to give you an idea of the reality of Rheality. And this is the oil and gas application, and the site is the same site 24 hours apart. So this was a Wednesday and it was a Thursday of the same week. It was March in Wyoming. So in the desert, it was one day, it was sunny and dry. The second day was snowy. But this is the environment we're working in, and we are currently applying the technology to. So in summary, and that's the last slide, really. Rheality is a smart sensor that is capable of measuring multiple features. Is inline, is in real time, is retrofittable, so it's easy to install. Is ubiquitous, so potentially, I mean, it can be used in many points of the same production line to map out the process, stage by stage. Is machine learning based, so it learns and becomes more accurate with time. So offers the perfect combination of flexibility, adaptability, and accuracy. So I think that's the end, and I will welcome any question, and please. Thank you.
Thank you very much, Francesco, and Federico as well. I've got a few questions I can ask you. Perhaps if I could start with you, Federico. You mentioned about training of a machine learning algorithm. Is that specific for each use, each different application, different type of mixture of fluids and solids and so on? And is your device self-learning in an application? Does it remember what's good and what's bad and then recognize it in the future?
Yes, so I think it's generally, so the machine learning, and we use obviously to derive, let's say, indirect measurements relate to the rheology. And yes, so the system obviously more things see, more clever becomes. And obviously it's a continuous learning. And the other things that we are working is obviously if in a way to use this technology to provide a way to derive some predictive model, because we can as Francesco and myself stress out, so we can actually we can record a lot of information at the same time, but obviously all those information we cannot let's say immediately understand to what they might depends. But with time and with recording, all those information can be stored and used as a library to understand what is going on in the process and recognize when things happen again and possibly understand what was wrong in the process.
Right, that's great. I was going to have a follow-on question for you, which was this sequence of 10 parameters. Mm-hmm. What are they and how do you derive them? But I think I know what your answer is going to be to that. But I've got a much more clever question from a potential customer of yours, actually, or somebody I know who works in the oil and gas industry. He asks, do the RRF parameters relate to any physical, meaningful parameters?
So itself, they are related to physical parameters, yes. But yeah, I cannot say more than that.
And also the following question is, you have to have flow and shear to generate sound. Mm-hmm. Are you at all sensitive to yield stress or gel properties?
So this is other things that we are trying to investigate in terms of, I think is potentially, I think is the aim is to be able to measure such effect, because obviously such properties of the fluid will affect drastically the fluid flow. So and then yes, I think is in a way, in a good way, not in the bad way. So I think is the aim is to be able to track when, for example, the jellification happen in a specific fluid, because obviously the pressure field will change dramatically and the sensor will read a completely different signal. So
that's a characteristic which you can use rather than something that hinders you as such.
Yeah.
Great. And I've got a question for Francesco as well. Given that there's not really been a way to do this in many industries prior to this type of device, how quickly or how ready do you find industry to adopt the idea of using real-time control when previously they've had to just use batches and test that the batch is good?
Okay, so the idea of what we experienced is that the idea is immediately appealing to them. So there is a strong need, and they know there is a strong need. However, as you said, there is an inertia due to their equipment and also cultural inertia on any change, right? Yeah. So what we are doing at the moment is a set of trials that gives them with a relatively small budget, gives them the confidence that if they have to move towards a bigger step, they have the rationale and the motivation to do so. Secondly, we kind of fitting into their strategic pillars for many industries, which is digitalization, before innovation and optimization of their production lines. So we fit into quite a few streams of strategic importance. So that's why there is a sort of sensitivity to what we propose, and there is a willingness to give it a try. Yeah. So at the moment, that's the entry door is through trial, but that shows they want to look beyond. They are looking beyond what they are doing at the moment. Right. Of course, changes by sector. So there are more sectors which are more conservative and sectors which are more kind of projected to the future, and we can see that. But overall, yeah, there is an attention to what can be done better.
Yeah, it's an interesting area. Another question here, do you take any measurements to deal with interfering noise sources in the pipelines?
Yeah, so yeah, that is often the sort of first question, and I think that is in a way is it's dealt with the RRF. So it's because, as I mentioned, the raw data is a very rich data set, and is a multi-frequency measurement. So the noise, in a way, can be located pretty quickly.
Yeah. That's great.
So yes.
Yeah. Okay. So you can cancel it out by the analysis method that you're using effectively. Yeah.
Yeah.
That's good. Well, I haven't got any more questions in the box at the moment, so I think I can just say thank you to Federico and Francesco for joining us this evening, and thank you everybody for joining the seminar. We'd love to have you come and join us for upcoming events, and there are many other events, of course, hosted by other regions and nations of the Institute of Physics. Just visit the events.iop.org website and head to iop.org if you're interested in becoming a member or learning more about the Institute of Physics and what it does around the world. And look out there also for our next talk. There's also a quick survey at the end of this. I know everyone likes to click away from them, but please do leave some feedback. We're always interested to hear if anyone's got any suggestions as to how they'd like the events to be different or to change in how we organize them. From me and from Federico and Francesco, thank you very much, and we'll see you next time. Bye-bye for now.
Take care.
Thank you. Bye-bye. Good evening.
Bye.